Hello and welcome to this third and final lesson on acylation reactions, at least in the context of nucleophilic addition elimination. So the focus of this lesson, which is going to be a shorter one, is on the reactions of acid anhydrides. I said in that first lesson that this is kind of a more minor part of the acylation reactions because you're far more likely to encounter an acid chloride reaction, and that's still true. The mechanism is not really required for AQA A level. I'm always a little bit nervous about saying that because AQA do have a tendency to sometimes spring things on you that are slightly off spec, and give you a little bit more help just because it's a bit more unfamiliar. But generally speaking, this is true. The most likely context in which you'll encounter acid anhydrides in questions is about required practical 10A, which is the synthesis of aspirin or some related synthesis, and it's usually in the context of the sort of question of whether to use ethanoyl chloride or ethanoic anhydride for that synthesis. And I'm not going to go through that now, that's something for a lesson about that practical, but that's the most likely context. Having said that, you could be asked to do equations for acid anhydride reactions, and I am going to go through the mechanisms, although I'm going to go through them fairly quickly. So you can almost consider the mechanism part of this lesson to be, I don't want to say optional, but less important, okay? And it isn't going to be explained in real, significant detail, but the equations task at the end is something that you should definitely have a go at. So let's have a look. We've got ethanoic anhydride and water, okay? So the mechanism is already set up, right? I'm just going to talk through some important points. So, when you do your acid chloride mechanism, your leaving group is chlorine, right, which leaves us a chloride ion paired with hydrogen usually, all right? That leaving group is now represented by this entire section. And if you go back to the very beginning and you look at the sort of generic structure of an acylating agent, there's a Z in place of either the chlorine or this, right? So that makes it look really complicated. In reality, it's not, right? It's still exactly the same series of kind of, curly arrows, but it makes it look more complicated because this is our leaving group, which is a big bulky thing, okay? So, right, we've got 5 curly arrows, just like before. We've got nucleophilic attack of the water on the carbon. We've got movement of a pair of electrons onto the carbonyl oxygen. We then have our intermediate, in which we show the double bond reforming. We get the leaving group leaving and taking the pair of electrons from this covalent bond with it. And we get a hydrogen leaving as a hydrogen ion and not taking any electrons from this covalent bond. So it's that thing of one of them leaves as a positive ion, one of them leaves as a negative ion. Okay? So this is exactly the same thing. If you box this whole section off and replace it with Cl, you've got exactly the same mechanism as ethanoyl chloride and water. There are a few kind of twists though, right, and I will give you a little bit of an opportunity to have a go at some of these with them set up as we go along. So, the products of this reaction are kind of interesting because we've got ethanoic acid on the left. Okay, you should be able to spot that very easily. Year 13 organic chemists, you should be able to name that very quickly, ethanoic acid. The implication is that that's come from this section. Okay, the idea being that if you take away this hydrogen and you reform this double bond and this is left, then you're left with ethanoic acid. So it's meant to represent that section of the intermediate after it has gone through this series of electron pair movements. Then your hydrogen ion is supposed to be down here, and the leaving group leaves as an ethanoate ion, and so that's supposed to be down here. In reality, just like in the acid chloride equations or mechanisms, you would pair the positive and the negative ion as an entire compound. In this case it would be ethanoic acid. So that's interesting because we've got ethanoic acid on the left, ethanoic acid on the right. In other words, when we write the equations, we basically get 2 moles of ethanoic acid from the reaction of ethanoic anhydride with water. You can apply that to any sort of symmetrical acid anhydride, and that's what the second equation is supposed to imply. So that's relatively straightforward, apart from the fact you get 2 of the same thing. That's a little bit unusual, but actually the movements of electrons are not that bad. Having said that, like I said already, the mechanism's generally not required in AQA levels, so if you struggle to get your head around them, it's not the end of the world. Okay? One more thing on this. Back to the beginning. Ethanoic anhydride and water produces 2 moles of ethanoic acid, right? But when we first learned about acid anhydrides, we learned that if you put 2 carboxylic acids which are the same together, then you might get a symmetrical acid anhydride and water as a byproduct in a condensation reaction. This is the reverse of that, and so that's going to be classified as hydrolysis. It's a hydrolysis reaction. This is the hydrolysis of ethanoic anhydride, and it occurs via nucleophilic addition elimination, but we classify it as a hydrolysis reaction. Or you could call it an acylation reaction, saying that the water has been acylated, but it's a bit weird to describe it that way. Okay? It's probably reasonable to assume that actually this exists as a reversible reaction or a dynamic equilibrium. I don't know what changes the sort of, position of that equilibrium, but it's kind of reasonable to assume that there's at least a bit of back and forth in that reversible process. So then let's have a look at the next one. Ethanoic anhydride and ethanol. So if you want to, you can now pause the video and you can have a go at completing this mechanism. It's nearly done, because we've got the structure of the nucleophile, the acylating agent and the intermediate, but if you want to, you can have a go. If you haven't had a go, then you can just watch me do it, right? I've got movement there, as usual. Showing my nucleophilic attack is going to be a little bit awkward just because of where I've positioned my nucleophile. I want a decent curve on that arrow and to make sure it ends up at the carbon. Then we're going to have another 3 curly arrows on here again. Okay. Same series of movements as before. Might look slightly different just because of the orientation of everything, but it's still the same. Then our products this time are different. They're not the same thing. You should be able to classify the organic product on the left as an ester, specifically ethyl ethanoate, and the thing on the right is ethanoic acid again. And you might start to notice actually that ethanoic acid is often the byproduct in these reactions, just like hydrogen chloride was often the byproduct in the previous set of reactions. So we get an ester and a carboxylic acid in this case, and we've acylated our ethanol. So, equations, right? We had ethyl ethanoate and ethanoic acid, and then your generic version, as usual, looks something like that. So I'm not going to dwell much on this, right? It's very similar to the acid chloride reaction, just with a difference in the byproducts and a difference in how the mechanism looks, even though the way it proceeds is actually identical. Here's another one for you to have a go at if you want to. Feel free to pause the video and have a go at completing the kind of electron pair movements in this mechanism. If not, I'm going to do it. So it's exactly the same. Okay, again, I've not got as nice a curve on that arrow as I would like, but it'll have to do given where I've put my ammonia. Then, same series of movements here. Secondary consideration is just like with the acid chlorides, when ammonia is your nucleophile, it can act as a nucleophile like it does in this first step, and it can act as a base like it does in that second step. And I've marked it in green because, if you remember, I said it doesn't need to form part of the mechanism, and the only reason I mention it is it will probably have an impact on the byproduct, okay, on the identity of the byproduct. So let's have a little look. So this time we're going to get an amide on the left, specifically ethanamide. And on the right, it's reasonable to assume that you'll get an ammonium ion, because when the ammonia molecule acts as a base, it forms NH4+, because it is a proton acceptor. And the ethanoate ion will probably pair with that. This compound would be called ammonium ethanoate. And again, there's a parallel there to the one where it forms ammonium chloride in the acid chloride reactions. Okay? The reason we have to talk about that is in the equations we need 2 moles of ammonia. Alright? And if I don't explain that sort of dual role of ammonia, then you might wonder where the second mole of ammonia in the equations comes from. So for this reaction specifically, it was ethanamide and ammonium ethanoate. You can apply that to your generic version as usual. Okay, so final mech, we've got ethanoic anhydride and ethylamine. This is just like with the acid chlorides. Feel free to pause the video and have a go, and also feel free to, when you pause the video, also have a go at naming the organic products. So whether you've had a go or not, same movements, same movements. This time we're not going to have our amine hanging around to act as a base, even though it would be more accurate to do so, just because the AQA don't require this, right? And they don't require it in the equations either, so I'm not going to put it in those. But just to be clear, there would be another molecule of ethylamine if there's enough of it around, if there's a reasonable excess of it, hanging around in this section down here, ready to pluck this proton off and to form an ethyl ammonium ion, and you would then get ethyl ammonium ethanoate. But because it's not needed for the equations, it's not going to be included in this version. So the product this time is another amide, but it's an N-substituted amide. You should have had a go at naming this, regardless of whether you've had a go at doing the mechanism or not. Quick reminder that this section has the prefix N-alkyl, and this bit is alkanamide, so to speak. So you have to count the number of carbon atoms, and we have N-ethyl ethanamide. And our byproduct is ethanoic acid. I'm not going to write that on because we've seen it a few times already. Okay? So that's an N-substituted amide. It's exactly the same products as what you get when ethylamine reacts with ethanoyl chloride. Equations. That's a bit confusing looking. Let's just get rid of that. Running out of space a little bit here. Okay, we've got N-ethyl ethanamide and ethanoic acid, and then your generic version as usual. I'm just going to, while we sort of finish up with this section, repeat myself and say that I don't think it's worth learning these by rote. I think you're far better off understanding the structures of the acylating agents and understanding the nature of the mechanism, and then trying to deduce what the product is, because there's so many different variations of this. It really doesn't it really doesn't bear fruit to spend all that time learning the various combinations, I don't think. If you disagree, you want to do it, it's fine, but I'm just sort of providing what my opinion. So here's the last part of the video, essentially. Task: pause the video and have a crack at writing the equations for the following combinations. Notice the red, which is code for danger, that's just basically me having a laugh by the time we get to that stage. In other words, they're starting to get really hard. Acid anhydrides are tricky anyway, but by the time you get to 5, things are starting to get quite difficult for multiple reasons. Okay, so really they're only there if you want to challenge yourself. Okay, so pause the vid, 1, 2, 3, 4, and if you feel like it, 5 and 6. So then, answers, only for people who've actually had a go. We've got 1 and 2. I've named the product. I've run out of space, so I had to go onto a second line. But your equation should look like this. Pause the video and check your answers. Three and 4. We've got another slightly tricky N-substituted amide in 3. And again, in 4, we've got to watch out that we've got 2 moles of ammonia and that we're forming an ammonium salt, not just methanoic acid. Just to sort of point about 4, by the way, it's got methanoic anhydride in it. For whatever reason, I've got a gut feeling that that's probably not a very stable compound. I might be wrong, but what I'm getting at is you probably wouldn't encounter methanoic anhydride as an actual, lab reagent very often compared to, say, ethanoic anhydride. But it'll do for an equation. It doesn't matter. It really doesn't matter. On to 5, which was me, like I said, just basically having a laugh. Things start to get a bit more complicated here. The first reason for that is that the acid anhydride is asymmetrical. It was butanoic propanoic anhydride, so you can't write the condensed formula in the same way. I've written it that way. It doesn't actually have to be written that way, but that was the most logical way to me. Try drawing it and you'll see what I mean. The second complication was that propan-2-ol is a secondary alcohol, and as soon as you make an ester from a secondary alcohol, you give yourself a harder time naming stuff. And so the butanoate part is straightforward enough. That's that section. Remember, it's the bit that resembles the carboxylic acid, so that looks a bit like butanoic acid, butanoate. Then we've got methyl ethyl, just to explain where that comes from, right? I'm not going to draw the whole structure because I don't have room, but if propan-2-ol is added to your ester, then you're going to see this, because the OH, where the reaction happened, was on carbon 2 here. So that's what I've drawn that's what I've written in the condensed structural formula. The way we name this is, we still look at the longest carbon chain, which is 2 carbons long, ethyl. We have to mention that there's a methyl group on it, methyl, methyl ethyl, no number necessary because there's only 2 carbons, and if you stuck it on the end it'd be propyl butanoate, but that's what we call it, methyl ethyl butanoate. Again, that's definitely on the challenging side, having to name esters derived from secondary alcohols. Okay, we get a similar problem in the next question. So we've got ethanoic anhydride, that's okay, but then we've got dipropylamine. So dipropylamine, this substance is a secondary amine. You might not have learned about amines yet, okay? But the idea is that instead of it just having NH2 on the end, the nitrogen's actually attached to 2 separate alkyl chains, okay? That's going to make an N-substituted amide, this thing here, and then you get ethanoic acid as your byproduct, but naming the amide is again a little bit tricky, and this time we will actually look at how its structure appears. I'm going to condense it slightly just because I don't have loads of room. So just to be clear, C3H7 is representing CH2, CH2, CH3, in other words, the propyl group, okay? And there are 2 of them attached to the nitrogen, so I've drawn 2 of them in my structure up here. So, this is an N-substituted amide, but the way we would name it, the first bit is the easy bit. Ethanamide. Because remember, your routine is to think, okay, which bit is kind of, which bit contains the carbonyl group, that's the alkanamide part, right? Ethanamide. Then you've got two propyl groups, so we're probably going to have to say, dipropyl somewhere. But the way that it works in this case is you have to put N, N dipropyl. And the idea behind that is that you are saying that both propyl groups are attached to the nitrogen. They're both, substituted onto the nitrogen. Like with the esters, naming amides derived from secondary amines is difficult, right? And it's definitely on the challenging side. So if you got to this stage and you've had a good go at these, even if you couldn't quite get it right, then well done you. All right, that's it.